to be introducing our next plenary speaker, Professor Tony Kai from Department of Statistics at UPenn. He graduated from Cornell in 1996. He joined Purdue, but then he changed both his research area from wavelets, not changed, but modified a little bit. So these days he's working on statistical inference on high-dimensional covariance structure, and also he changed his institution. So he is Dorothy Silberberg Professor of Statistics at Wharton School. He has held many associate editor and editorial positions. Recently, he just finished a 3-year term as the editor-in-chief of Annals of Statistics. He's a fellow of Institute of Mathematical Statistics, recipient of many awards. He's a medallion lecturer of the Institute, as well as a recipient of the 2008 COPS Award. So without further, actually I have a little bit of extra information. Apparently statistics is in his family's genes, because from what I understand, his sister is also a biostatistician. So with that, I give you Professor.
Thank you very much for the generous introduction. It's great to be here, especially in the wintertime. It's nice to spend a week in West Coast. And so today I'm going to talk about high-dimensional problems, especially on inference on covariance structures. So first of all, the talk is based on joint work with a number of people, and Harry Zhou is my long-term collaborator, and so is Ming Yuan, and Wei Dong and Rossi, they were my former postdocs. And from other sessions in this workshop, we can tell that there are more and more problems with high-dimensional data. And the problems statistically can be very roughly divided into 2 kinds. One kind is the main object of interest is the mean structure of the distribution. And examples, many examples, for example, say high-dimensional regression, we will try to understand the mean structure. And compressed sensing or signal detection. In genomics, an interesting problem is what's called copy number variation analysis. And all these type of problems, the main focus is on the mean structure. In addition to that, there's a number of other problems where we not so much interested in the mean structure itself, rather we want to know the relationship among variables. And for this type of problems, we are interested in knowing the covariance structure. And there are many problems of this kind. For example, in terms of statistical methods, like principal component analysis, you work on the covariance matrix directly. And in some other problems, like classification or clustering analysis, we want to know something else. But it would be very nice if the covariance structure is known. So in all these type of problems, we either want to know the covariance structure itself, or we want to use the covariance structure for something else. And there's many applications in different areas. And I don't want to go through them one by one. I'll mention some of them more specifically in a moment. Now here's a toy example about the graphical model for Senate voting. And in this case, we want to know who are voting along what line. And this is a toy example, and you can see that most of them vote along the party line. And same is true for, instead of people, we can have genes. And we want to know, say, gene regulatory network. And we also want to know the relationship among the genes. And more specifically, for many statistical problem, we need to use the covariance structure. And one simplest example in classification is this linear discriminant analysis. And it's very easy to understand. We have 2 samples, X sample from one normal population and a Y sample from another normal population. And we want to classify a new observation. So you can think of X as measurements on patients with certain disease and Y on healthy people. Now comes this new person called Z, and you want to know whether the person has a disease or the person doesn't have the disease. If we know all the parameters, mu1, mu2, and sigma, then life is nice and simple. We have the optimal rule, the facial discriminant. We compute this quantity, say Z is a value of the observed value, and mu bar is the average of mu1 and mu2, and you compute. If it's positive, you classify into the first class, and if it's negative, you classify into the second. But of course, in real life, you don't really know those quantities, mu1, mu2, and sigma. And as statistician, we estimate. And we can estimate mu1 by x bar, mu2 by y bar, and we estimate the inverse of the covariance matrix by the inverse of the sample covariance matrix. And that's in classical multivariate analysis. And all is well if the dimension is small and sample is large. And you can derive many interesting properties of this rule. The problem is what to do when P is very large. So throughout the talk, P indicates the dimension of the problem, and N1, N2 are the sample sizes. And first of all, when P is really large, the sample covariance matrix is not even invertible. So you have a problem. The problem is mathematical. How can we invert a non-invertible matrix? And of course, it's also it's statistical, because there are all sorts of numerical studies indicating that even when N1 and N2 are relatively large, say they're equal to 500, and P is, say, 30, you already have the problem. The reason is the matrix is 30 by 30. That involves 900 elements, or you divide by half, it's 450. And the method is already very unstable. So when P is really large, of course, you need to do something else. In here, in this problem, we have conveniently assumed that those two covariance matrices are the same. But in real applications, how do you know they're the same? So even this testing problem turns out to be highly non-trivial. And when they're not equal, by the way, the linear discriminant is not a good method. It can fail. And there's certainly a wide range of applications for this type of classification problems. And another kind of problem, we can think in terms of portfolio optimization. Suppose you have 1 unit of money and you want to invest, say, over P possible assets. And suppose the return is called X, which is random, and the allocation vector is W. So expected value of X is mu, and the covariance of those return is called sigma. And again, if we assume mu is known, sigma is known, then we can solve this problem relatively easily, because everyone wants to get a high return with small risk. So given a target return called C, we want to minimize the variance, the risk. And if mu and sigma both are known, then this can be solved explicitly, and it's a very nice, simple solution. And of course, again, in real life, you don't know mu, you don't know sigma. And if you happen to know those, you shouldn't be here. So the question is how to deal with the problem if we don't know mu and sigma, and when P is large especially. So you have exactly the same question. What to do when P is large? And you can no longer, for example, replace sigma inverse by the inverse of the sample covariance matrix. So in all these type of problems, we need to know something about the covariance matrix or its inverse. And if we think about this more broadly in terms of statistical problems, one class of problems is about estimation. We want to estimate something about the covariance matrix. So either we want to estimate the covariance matrix sigma itself, or in some applications, we want to estimate its inverse. And mathematically, they're equivalent. It turns out statistically, they're not. And typically, if you're interested in estimating, say, omega, which is sigma inverse, it's not such a good idea to estimate sigma first, then invert that estimate. And sometimes, for example, in Gaussian graphical model, you might care less about the matrix itself, but you do want to know the support. And as we will discuss later, the support gives us the graph. And in some other problems, you don't actually want to know the whole matrix, but you want to know some functionals of the matrix. And I will mention a few examples in a moment. And you can also have testing problem. And one testing problem I mentioned a moment ago is that you have two populations. You just want to know whether the covariance matrices are the same or they're not. Or in the one sample case, for example, you want to test whether sigma is identity or sigma is diagonal. Or in some cases, in time series analysis, for example, you want to test whether the matrix is banded. If it's banded, then there's no long-range dependence. So the whole list of problems. And of course, the more problems, you simply want to use the covariance structure for something else. So you want to apply the knowledge of covariance structure for, say, classification or portfolio optimization or dimension reduction or long list of problems. And it would be very nice if you know the covariance structure. But of course, we don't know, so we need to do something. And this talk, I'm going to focus on estimation. And as I mentioned earlier, that many estimation problems, I'll mainly focus on estimation of the whole object, either the whole covariance matrix sigma or the whole precision matrix omega. And other problems, for example, you want to estimate the singular vectors. You want to do PCA. And there will be a session after this on estimation of large matrices, and Zhongming will talk more about PCA. And for some other problem, you want to estimate some other functionals, for example, the leading eigenvector. Now, the problem can be stated relatively easily. So imagine that we have IID sample drawn from some high-dimensional, p-dimensional distribution with covariance matrix sigma. And we want to optimally estimate the covariance matrix sigma based on the sample. So the goal is very easy to understand. And of course, the classical estimate, the most natural estimate is the sample covariance matrix. And that's very easily computable. And on the other hand, it's also by now well known that sample covariance matrix is not a good estimate. And there are all sorts of problems with the sample covariance matrix. And initially, certainly, those are very interesting and very deep results. But you can see the difference here between mathematics and statistics. In mathematics, it will be a great result if you have very strong negative result. But in statistics or in engineering, typically it doesn't work. If you tell people that, say, you shouldn't use sample covariance matrix, then the next question must be, what should I use? So the question is, if sigma star, the sample covariance matrix, is not a good estimate, what's a good estimate? But unfortunately, when the sample covariance matrix doesn't work, there's no other estimate that works universally better than the sample covariance matrix. Just imagine there is. It's a very simple proof. If there is one, we should have used that thing long ago, and we didn't. So it turns out that when sigma star is not a good estimate, it depends on the underlying truth, the structure of the underlying truth, and quite a few covariance matrices that has been well studied in the last few years. One class of covariance matrix is what we call bendable covariance matrix, and which arises naturally in time series analysis, where you can think of the covariances decays as you move away from the diagonal. So if you have two variables that has long leg, then the dependence becomes smaller and smaller. Another kind of, but here the variables are ordered. So you have one variable, you have neighbor and next neighbor and so on. And in some other applications, you don't have natural order, but it's reasonable to assume that covariance matrix is sparse. Sparse means that every row and every column is a sparse vector. So only a few of them are non-zero, and most of them are zero. If you have, say, stationary time series, then the covariance matrix is turbulent. Turbulent means that every diagonal has the same value. In many other applications, we are not interested in the covariance matrix themselves, we are interested in the inverse. And because of connection with Gaussian graphical model, a very natural and interesting class of precision matrix is the sparse precision matrix, which we will discuss in a moment. And these are certainly not new problems. It has been studied in the last maybe 5 or 10 years or so. It's quite recent in terms of this high dimensional setting. And the papers by Baker and Lavina, those two papers are the first, gives explicit rate of convergence in this type of setting. And there are other papers that introduce a lot of methodologies. And if we think about this problem, one might ask the first fundamental question is, for a given problem, how hard is the problem? In the sense that we want to know, for a given class of matrices, we want to know what's the minimax rate of convergence. And for practical application, we also want to find optimal procedures, some procedure that's nice and easy to use, such that it's rate optimal. So the performance of the whole class is within a constant factor of the optimal rate. And it turns out that typically the optimal estimate depends on the specification of this class theta. So you give me a theta, I can give you an optimal estimate. But typically, if you don't know the covariance matrix, you don't really know the properties of that matrix. So a third goal is try to construct an optimal and adaptive estimate of sigma such that it doesn't rely on the underlying parameter for the parameter space. And we will discuss all these three in a moment. So we'll start with the discussion on bendable covariance matrices. And then I'll spend some time to discuss sparse precision matrices. And these two problems are quite different, as we will see, in terms of both in terms of the methods and also in terms of theoretical analysis. So bendable covariance matrices, I refer to this type of matrices where sigma ij, the covariance between the i's and j's variable, decays as a function of the lag I minus j. And this alpha indicates how fast it decays. Yeah, if you're familiar with, say, function estimation problems, this alpha is very similar to smoothness in function estimation problems. And in a paper I did with Chunhui Zhang and Harry Zhou in 2010, we show that the optimal rate of convergence for estimating this class of covariance matrices is given by the expression here. It has two terms. One term depends on alpha, the smoothness, and there's another term that has nothing to do with alpha. And then initially it was somewhat intriguing to us, but once you think this through, and it turns out to be quite natural. So this term, log p over n, doesn't depend on alpha. So you can take alpha to be infinity. That means that you look at a class of diagonal matrices. And even for diagonal matrices, you always have this term. Oh, by the way, this norm is a spectral norm. It's the largest eigenvalue. And this term tells us what's the dependence on the difficulty of the estimation problem on this alpha. And typically, it's true in other settings. The larger the alpha, the easier to estimate. In terms of the optimal procedure, maybe I show you the picture, it's easiest. So think about this whole thing, whole block as the sample covariance matrix. Because we know that the covariances decay as you move away from the diagonal, it makes sense to truncate at some point and set everything beyond those two bands to 0, because it becomes less and less important and the noise level stays the same. And another class of estimates, this class is called bending estimate. Another class is called tapering estimate, where you don't set them between 0 and 1 in terms of weight matrix. You do a gradual smooth decay. It turns out that it doesn't really matter which method you use. The key is to choose the size of the band correctly. And the size of the band is given by n to the power 1 over 2 alpha plus 1. And that's a nice estimate, but there's some downside to this. But before I mention that, I want to emphasize one thing, that what's a matrix? A matrix consists of many rows and columns. Then a very natural method approach to matrix estimation is try to estimate every column or every row separately. Right? Once we do that estimation, we assemble them together, give us a matrix. It turns out that for this class of covariance matrices, these two problems are fundamentally different. In other words, optimal estimation of the rows and the columns separately. Once you put them together, it doesn't give you an optimal estimate of the whole matrix. So these two problems are not the same. You have to take into account the whole matrix, the structure of the whole matrix together instead of one by one, one row or one column at a time. Now let's go back to that estimate, the bending estimate and the tapering estimate. The bending and tapering estimate requires the choice of this bandwidth or tapering parameter k, which is n to the power 1 over 2 alpha plus 1. So you need to know alpha. If you don't know alpha, you don't know how to choose k. And if you choose the wrong k, you will get a suboptimal estimate. So the question is, the optimal choice of tapering parameter depends on alpha, which is unknown in practice. So the question is it possible to construct a single estimate that doesn't depend on alpha, but it does as well as if you know it, for a wide range of alpha, say for all alpha positive. And if you think about this problem and if you make connections to other statistical problems, one natural approach is try to do adaptive bandwidth selection. If you find some way to choose this k adaptively, then you're all set. And we still believe that's a feasible way to do it, although we don't know how to do it at the moment. So we are going to, first of all, the answer to the question is yes, otherwise I wouldn't be talking about this problem. But the strategy is completely different. We are not going to try to come up with an optimal bending estimate or tapering estimate. Instead, we are going to take a completely different approach by carefully divide the sample covariance matrix into blocks. And I'll explain in a moment what do I mean, and then apply thresholding to each block. So it takes 3 major steps. The first step is the construction of blocks. And it turns out the blocking itself, it requires some tricks, because we don't want to divide the whole matrix into blocks of the same size. In other words, we don't want to cut the whole matrix up into small, same size pieces. We want the block size to grow. As you move away from the diagonal, the block size should get larger and larger. And once you make the block size not equal size, you have a problem, a small problem. It's almost like solving a jigsaw puzzle. You have many, many pieces. How can you put them together so that you can get the original square back? And more technically, what's more important is that, as I mentioned earlier, we have to consider the whole matrix together. We cannot look at, say, them element by element or row by row. So in terms of analysis, we want to assess the effect of the estimate based on the joint effect instead of element-wise. And the main difficulty of the technical difficulty is that the spectral norm is not additive. So the error you make for the whole matrix is not the sum of the elements. So how do we divide? So instead of describe the procedure, I just show you the picture. So along the diagonal, I'm going to take very small size block and say take k naught by k naught. And you do this along the diagonal. So you have many, many small blocks. Then on every odd row, I want to put 2 small blocks of the same size. On the even one, I only take 1 more. So in other words, I only have these 2. That gives me space to double the size of the block. So I have a block of twice as large. And I do exactly the same. 3 in a row on the odd rows, and on the even ones, I have 2. And that again leaves me enough space to double the size again. And I'll do this all the way till the end. Now, this of course is just one step. By blocking them, I want to do something with a block. And what I want to do is thresholding. Because I need to decide whether a block is important, contains enough signal, or the block is not important, not uninteresting. So I need to find a way to decide whether I should keep this block or set all the elements to 0 for that block. And that depends on the dimension of the block and also the corresponding spectral norm of that block. And in more detail, there are 3 different kinds of blocks. Everything along the diagonal, I don't do anything, I keep. Everything that's far away from the diagonal, if they're sufficiently far away, then the block size is sufficiently large. If it's larger than n over log n, I kill. So I set those far away blocks to 0. So how far away is determined by this simple rule. And what's more important are those blocks in the middle. Not too small, not too big. I'm going to threshold. And the way to threshold is for each block called B, I want to calculate its spectral norm, the largest eigenvalue for that block. And I compare that with the estimate variance of that block. If the size of the signal is significantly larger than the variance, I will keep that whole block from the sample covariance matrix. Otherwise, I set them to 0. Every element in that block to 0. And here, everything is fully specified. Lambda 0 is a constant. You can take this to be 6. And those are the corresponding diagonal blocks you can compute. And D of B is the size of the block, and P is the dimension, and N is the sample size. So in this whole algorithm, there's no unknown parameters. And in particular, there's no alpha. So this whole procedure doesn't look at alpha at all. Now the question is, how good is the estimate? It turns out that if we evaluate the performance of this estimate over the class of bendable covariance matrix with decay rate alpha for any alpha positive, we will get this upper bound. And this upper bound to be exactly the same as the minimax rate. So in other words, we have a single procedure that achieves optimal rate of convergence for a full range of bendable covariance matrices without the need of knowing alpha. So such an estimate in statistical terms is called adaptive. Now, I don't want to get into technical details, but I do want to mention a few main steps. The first one is that once we cut the matrix into many, many blocks, we have large blocks and small blocks. And you should analyze the small and the large blocks separately. And the key observation is here. Although initially I emphasized over and over again, saying in large dimension, the sample covariance matrix is not good. And it's still true. But if for any reason you only want to estimate a small, say, block of the true covariance matrix, then the best thing you can do is steal the corresponding block from the sample covariance matrix. The catch is that the block size has to be small, relatively small. And once we carry out the first 2 analyses, it will tell us how well we have done for each block. We can get a fairly good risk bound for every block. But we still want to know how well we have done as a whole. And that requires a very neat but elementary inequality, what we call norm compression inequality. If you are interested in the details, it just appeared in the Annals of Statistics. So I want to mention this inequality very quickly. So suppose you have big matrix, and now you cut this matrix, write this matrix in the block form. So you cut it according to the rows and the columns. Now you have a block matrix. Now let's do a transformation. For each matrix, submatrix, say A11, we only compute its norm, say spectral norm. Then this is a big matrix, originally P by P. Now after you do this norm transformation, it becomes G by G. It's a number of blocks. And our analysis basically tells us how well we have done over such a matrix. But what's originally we were stuck because we couldn't go from this small matrix back to the original big matrix. It turns out that there's a very neat inequality that the norm of the large matrix will never increase. It will be always bounded about by this much smaller matrix. So if we have good understanding of this small matrix, we are set. So covariance matrices are certainly many other kind of covariance matrices. For example, sparse covariance matrices, Toeplitz covariance matrices. But we don't have time to go through those in detail. So instead, I'm going to switch the topic slightly to estimation of precision matrix, which is the inverse of the covariance matrix. In some sense, estimation of the covariance matrix is relatively easy, or at least easier than precision matrix. The reason is, no matter what, the sample covariance matrix is an unbiased estimate of the target. So you have something to base on. You can threshold, you can do banding, tapering. But how can we estimate the inverse, knowing that the sample covariance matrix is not even invertible? And of course, even if it's invertible, typically it's not such a good idea to take the inverse and do something to the inverse of the sample covariance matrix. So the problem is as follows. We have an IID sample from a high-dimensional distribution, and with covariance matrix called sigma, and precision matrix, its inverse called omega. And we want to estimate the precision matrix optimally based on the sample, where we assume that the precision matrix is sparse. And we ask exactly the same kind of question. So what's the optimality? How hard is the estimation problem? And how to achieve adaptability? How can we achieve adaptation without knowing, for example, the exact sparsity of the matrix? But before that, I want to give you some motivation about why the problem is important or interesting. And one reason why the precision matrix is important is because of its close connection to Gaussian graphical model. So if we have a Gaussian graph, say, with a vertex set V and edge set E, and then those are variables, and if you have, say, an edge between two variables, it means that those two variables are conditionally dependent, given all the rest. And it's of great interest. We want to estimate or recover the structure of a graph for many, many applications. And in the Gaussian case, it's well understood that whether there's an edge between, say, node I and node J, it's exactly corresponding to whether the corresponding element, omega ij, is 0 or it's not 0. If it's 0, then there's no edge between those two nodes. And if it's not, then there's an edge. So recovering of the graph is equivalent to estimating the support of the precision matrix. And recently, many different kinds of extensions of this type of results. So you don't really need to have, say, normality. And it can hold over a more general class of distributions. Now, again, it's not a new problem, and this has been studied in the literature. in terms of, both in terms of the graphical model itself and also in terms of estimation of the precision matrix. And Peter Buhlmann and Manshausen, they developed a method called the neighborhood selection method, which works quite nicely for recovery of graphical model. And there are many methods based on penalized likelihood using the Gaussian likelihood. And there are other methods that's related to penalized likelihood but different, what it can be termed as constrained L1 minimization. And we will mainly be focusing on constrained L1 minimization. So let's think about the problem. We have available to us a sample covariance matrix, and we don't know the true covariance matrix. What if we do know the true population covariance matrix? If we know the true covariance matrix, then here without star, sigma is a true covariance matrix, then this omega is a solution to the equation that sigma times omega equal to identity, right? That's the definition of the inverse. But of course, we don't know sigma. If we know sigma, we don't need to do anything. But we have available to us sigma star. So we are going to replace sigma by the sample version sigma star. But of course, there's no hope that we will get a solution, or actually it's not desirable to have a solution exactly equal to the identity. So instead, we are looking for something called omega, such that when it's multiplied with the sample version, sample covariance matrix, it's not very far away from the identity. And also because of the structure of the problem, we know that the true precision matrix is sparse. And by the well-known relaxation, say from L0 to L1, we are going to minimize the L1 norm of the precision matrix subject to this constraint. And turns out that's an easy problem to solve. Because if you think about this for a second, you realize that this whole thing is decomposable. Because if we multiply this matrix with a column of omega, then there's no relationship among different columns. So we can solve this problem column by column. So take any vector beta. We multiply with this sigma star, and we want this vector to be not too far away from the ith unit vector in the standard basis. And if you're familiar with that